Hello and welcome to our lesson on inferences about proportions. So far in this class, we've done months and months of work on other things, inferences on averages through all different types of situations where we need different techniques, where we have lots of data or not a lot of data and all that. We're just going to kind of generally introduce this. And because of that, we should be able to get through a lot of material on making inferences about proportions today because of our background. All right. Now, where are we kind of going to start with this proportion idea? Let's kind of start with the idea that we would like to consider categorical data now. All right. We haven't really considered categorical data in this course up to this point. Now, we're going to go the simplest way to do this. The simplest type of categorical data is only with two categories. So, what we might think of as binomial like things. So, success, failure, in or out, yes or no. You have this or you don't have this. Only two categories. And we can do that with binomial distributions. Okay, we've studied binomial distributions. Here's the formula if we were going to do this by hand, which we did earlier in the course. We did some by hand, but thankfully now we have our functions built in and stuff to do all this binomial distribution stuff, not by hand, to save us some time and some stress. X, of course, is the number of people we're counting in the group we're looking at, whether that be successes or having a disease or whatever. Uh, the pi is going to stand for the probability of success, and n is our sample size. Earlier, I will point out in the course we used a lowercase p here, but the longer and deeper you get into the course, the more you have lowercase and uppercase p's floating everywhere and everything. And traditionally or classically, most textbooks use a pi in this formula. Just when you introduce it, especially like if you're teaching the intro freshman stats class, they panic if they see Greek letters. So lowercase p is used in some freshman textbooks. But higher level and classical textbooks all like to use lowercase pi. Not that it matters. You didn't need to know that. But anyways, so um, we're gonna want to start by making, like I said, inferences is the whole point on this. We'd like to predict pi. That's what the whole kind of tilt is can we predict what this pi is from our data? Okay. Well, that means we're going to want to make confidence intervals. And of course, the next place we've been going with everything after confidence intervals are hypothesis testing. Okay. All about pi. All right. Now, the good news is the best point estimate for pi is just the sample proportion. So we take a sample, we have our sample size, we see how many people have the trait we want, how many people said yes, how many people said, yeah, they have the disease, how many people had success, and we just divide those to get a sample proportion. We're going to call that pi hat. Okay, that's our sample one, that's our estimate. And if we want to make a confidence interval, I have some really good news. Remember, binomial distributions can be approximated by normal curves. Now, we do need to be careful when this gets to pretty extreme values, whether the pi be really small or really large, we might have issues. But if the pi is pretty, not extreme, binomial distributions can be nicely approximated with normal curves. That's also nice because we can work with continuous or pretend continuous data as opposed to discrete. Okay, now, since it can be approximated by normal stuff, that means I want to be able to find the mean and standard deviation. And these are just the textbook definitions of mean and standard deviation for binomial distributions using our parameters. And once we do that, we can find the confidence interval in the most basic of ways that we've been building confidence intervals. None of those weird formulas from like bootstrapping or anything like that. It's really simple. We just take our point estimate and we add or subtract our critical z-value times the standard deviation. Well, that's the generic type we've been doing the whole course, and that has a name that's just called the walled confidence interval. I've never told you the name of it. The reason I'm telling you the name now is probably in a little bit we're going to learn some other style confidence intervals for proportions, for estimating proportions. Okay. Now, I will say that we've defined this earlier up there, and I'm not actually going to probably know the distribution standard deviation because if I did know that, that probably means I already know the population the parameters, and then I wouldn't need to be making estimates on them if I knew them. So I'm going to have to use my estimates in this formula here to do the best we can. Now, whether that's a good or bad idea, we can discuss that later. But for right now, that's the best we can do. So we're going to estimate standard deviation using our estimates. Okay, so this is called the walled confidence interval, and we can do some really quickly. And I got some written up in R code, and this is nothing more than using R as my calculator. Really simple, quick, and easy, okay? So let's just say that we came up with some new treatment for cancer and we'd like to see how well people survive after taking it. So we get a bunch of patients, 870, they all have cancer and we give them our drug. 330 survive past some set amount of time. Now, whatever that is, if that's 5 years, 10 years, 2 days, whatever, I'm not paying attention to the details, just kind of soaking up how we would make an estimate for the proportion of people we expect to survive for however long we're looking at. So we get a sample proportion just by taking the total and dividing that into the number that have the characteristic of being surviving. And so let me run that line of code to put that in. Then I'm going to have sigma. That's just my standard deviation. That's just the formula from earlier for standard deviation. All right. So our point estimate's about 38%. Whether that's good or bad, we're not going to discuss it. And we get about 0.016 for standard deviation. So I just use the formula, take my point estimate, add and subtract now this comes straight from Z tables. If I want to use a confidence interval with alpha of 5%, 95% confidence intervals, these are the Z values, the critical values, and times sigma. So I can get my low side and my high side by adding and subtracting. And then you can see my confidence interval runs from about 34.7% to about 41%. Okay, so we're 95% confidence that that the proportions in between here. Careful with the wording, not exactly the best wording I've ever used for describing a confidence interval, but between 34 and 41%. Okay, now back to our notes. Well, if that's a walled confidence interval, when will I need another one? And I told you to be careful when pi gets to be extreme. Well, there's an issue. In dealing with estimating proportions, it doesn't even have to be not really that extreme. If your proportion is below 20 or above 80%, 20% and 80%, the walled statistic will become kind of not very good. Okay, now that's kind of an issue because that's not that extreme. I would argue that's not very extreme values. And so we're going to need something different. So what we're going to do is a different confidence interval, not a walled, but a different one. So this one is by Wilson, Agresti, and Cool. Okay, it's called a WAC confidence interval because that's a lot of names to write. So we just take the WAC. WAC confidence interval. It's a weird adjustment. So we're going to make a new X for our instead of using the normal X, we're going to add a little bit to it. Now this looks like a lot, but if you just kind of focus in, it's a critical value squared, that Z value squared, and then we're just going to multiply by half. Well, that Z value for 95% confidence interval, that's about 1.96, almost 2. 2 squared is 4, half of that would be 2. So it's almost like we're just adding 2 to the X, and then we're adding something to the sample size. Okay, and if you look at that, that's just that critical value squared. It's about 2 squared, so about 4. So it's almost like adding a 2 and 4 to the X and the N. That doesn't seem like it'd do a lot, but it's a little bit of an adjustment. If you think about what that is, if you look at like a fraction, because how did we find this proportion? It was the X over the N. And if you're adding 2 to this one and 4 to the bottom one, that's almost like kind of adding some, I don't know, the best way to word this was like kind of trying to make it closer to half. So we're trying to pull this away from the 20% and 80%, more towards the middle is what we're trying to do. That's what this adjustment does. And so we can run kind of the same style of stuff, and we just tweak our X and our N. So let me show you an example of that really quickly. So there's city investigating the speed of response for their water breaks. So they got 50 water breaks, and 43 of them were responded to within 1 day, 24 hours. So we're going to make a 95% confidence interval to predict the amount of water line breaks that get responded to within 24 hours. So here's my typical proportion. I'm calling it pi 2 because I have a pi up here somewhere. Pi 2 and my sigma. Okay. Now, this is my straight up estimate. What if, well, if I do a walled confidence interval, let's go ahead and get that. That's what this is. And you get about 76% to 96%. Okay. Now, if I wanted to do a whack, instead of going with this proportion, 43 over 50, I'm going to take 43 and adjust it with that formula that we saw earlier. Okay? And I'm going to take my sample size 50 and adjust it. Okay, this is just that z, the critical value squared times a half. Okay, and so then I can get a new proportion and a new standard deviation using those values and get my new confidence interval. And what do I get? I get about 74% to 93%. Well, how far off is that? That's not very far, but do notice that it did what I said and pulled these values closer to 50%, closer to the middle. Okay, that's what it's doing. It's just pulling you away from those extremes, kind of tightening things towards the middle. Okay, since both of these were over 50, it pulled both of them down some. Okay, now back to some more notes here. So one adjustment is that we have to pay attention to is we're asking yes/no questions. So consider this. What if we wanted to go out, and this is just categorical yes/no data, and ask people if they like ice cream or not? I imagine the percentage is pretty high, but it's not 100% of the population that likes ice cream, right? I don't know who those people are, but I'm sure there's someone out here who doesn't like ice cream. But let's say we go and sample 10 people. In the first 10 people we stumble across, we ask, I'm sure it's probably a pretty good chance you might get 10 yeses. And then your estimate would be 100%. Well, 100% is probably not accurate, probably definitely not accurate. Otherwise, there wouldn't be any reason doing the research. So how do I handle when I get all yeses or all nos? Or let's say I go around asking if people like liver. In the first 10 people I come to, all 10 say no. I'm sure the actual true proportion is not 0% or not 100% in the case of the ice cream. How do I estimate that? Well, there's just some simple formulas. So if everybody says all no and I get a 0 for my count, I use this as my formula for my proportion. Now notice this is dependent upon sample size and sample size only. If everybody says yes, I use this formula. So x equals n, that means everybody in the sample size says yes. I use this formula to get a good point estimate. Once again, notice that it is dependent upon sample size. Okay, I can also make confidence intervals in the same way. So if everybody said no, this is my confidence interval. I know the true value is close to 0, so I'm going to say it's between 0 and some other small value. If everybody says yes, I know it's almost 100%, so it's between some large value and 100%. So these are just straight up formula driven. Notice they're only dependent on our alpha and our sample size, or the sample size. That's all they're dependent upon. Okay, so we can do some examples of this. This is just straight up formula stuff, not real hard to see. So let's say we got a new PC operating system and we claim to be compatible with all other computer programs. So we made something other than like Windows or the Apple stuff. So we sample 50 computers and we're compatible with all 50. Great, that's pretty awesome. Okay, or 50 softwares, and we're compatible with all 50 programs. Okay, so let's give a point estimate. Well, 100% would not be a great point estimate. Since I got all yeses, I just use this formula where I take my 50 and I add 3/8 to it. That's the top of the fraction. And then I divide that, the bottom of my fraction, I take my 50 and I add 3/4 to it. Okay. And let me see what we get for a proportion. About 99.26 or 99.3. That's probably a more accurate estimate of how many programs this thing works for. Because there's got to be one weird program out there that won't work for it. Okay. Now if I want to make a confidence interval, okay, all I need to do is get the low value because I know it's going up to 1 or 100%. And so that's purely just based off of my alpha and my sample size. Okay, boom, boom. I get about 92.9, 92.88. So there's my confidence interval. That's the best we can do because our data was so extreme. We got all yeses that I need to just use these formulas to do something else. Okay, now that's almost everything that we want to cover. That's estimates and point estimates, and notice there's three layers of extremes there. There's just the plain walled when our pi is in between 80 and 20%. When we go further out, we need the WAC confidence interval with an adjustment. And then when we get really extreme data like 0% or 100%, we need to use this one other adjustment, just straight up formula driven, okay? Now, one last thing, we'd like to do hypothesis testing. Lucky for us, we do have R, so we're just gonna use the built-in binomial probability function to calculate p-values, because we're mature enough, we've done so many confidence tests in this class that if I can just give you a probability of how likely something is to happen using the assumptions of the null hypothesis, that's our p-value. And so that's all we're doing is looking to see how extreme things are. So if I am using R, it's as simple as this. For a left-tailed test, I just straight up use the binomial probability function built in with x in the hypothesized proportion. If it's right-tailed, I need to do 1 minus the p binomial function, and because this is discrete, pay attention to what we put in. Oops. Pay attention to what we put in for the x. Remember, we got to go down 1, x minus 1. The sample size in the hypothesis proportion. Now, two-sided is a little bit more interesting. So whenever our proportion estimate is above the hypothesis, we do 2 times 1 minus, almost like a right-tailed. And where it's below, we do 2 times the left-tailed thing, and that's how we come up with the two cases. Okay, 2 cases to consider there. So just using the p binomial function in R. Okay, so let's see some examples. See some examples of this. So example 10.5. So alcohol abuse by underage college students is what this one's about, and they show that the theorized the hypothesis is that 44% of college students binge drink. Okay, bad thing, bad for your health, bad for other people's healths. Okay, some college campus says we don't have that same problem, we're better than that. But you think they actually aren't better. You think they're worse. You think they have above average binge drinking, so you're going to design an experiment. So you go around and you just start sampling their people, and you found that 1,200 out of the 25 students, 100 students, binge drink. Is that enough evidence to reject that they're okay? Can we say they have a problem? So here's our null hypothesis, 44%, and we think that it's bigger than 44%. So this is a right-tailed test. So I'm going to use 1 minus the p binomial function, the probability of binomial function. This will tell me how extreme it is, assuming 44%, assuming the null hypothesis is right. Okay, now notice it's 1,200. I had to go 1 less because this is right-tailed. And if I run this, I'll get my probability, my p-value, which is a pretty strong p-value. It is 4 zeros after the decimal than a 3. So that's strong evidence we can reject their claim. No, they are not better off. They do have a worse. We can argue that their problem is actually worse than average. Okay, and all we had to do was find a probability, how likely it is, and based off of the null assumption, that's our p-value, it's smaller than our alpha. I didn't define an alpha. I told you we're lazy in this class and always just let alpha be 5% unless we need some other thing to look at. Now let's do another example, just no context, just a left-tailed one. So if the probability, so the null hypothesis is it's 20%, you think whatever we're talking about is less than 20%. We take a sample and 10 out of 70. That seems less than 20. So let's do a probability test here. We get a hypothesis test. We get the probability using this binomial function, and we put in our x and our sample size, and the hypothesis, the null hypothesis. That's important, using their assumption that we're trying to disprove as the actual proportion. And if I run these, I get a p-value of about 15%. That's not really extreme. That's not strong enough evidence to reject the null. So we have to accept that the null is correct. We cannot disprove it. Okay. So there. That's our intro into this estimates on proportions. Okay. Inferences about proportions. We can make confidence intervals, we can make point estimates, and now we can do hypothesis testing. That's all we need to know. So until next time, take care.